To your first lesson of the new year. I'm sure you're just as excited as I am. Take that as you will. Okay, today's lesson, some of it is going to be stuff that's familiar to you, and some of it will probably just be a little bit more specific into stuff that's already familiar to you. So first we're going to start off with the triangle inequality. Okay, here's what we got going on. Basically, this is talking about the relationship of side lengths in a triangle. And so I'm going to demonstrate with, I'm going to actually have you fill in the blank. The three sides to make a triangle. The sum any two sides needs to be the remaining side. And I want you to see if you can fill in the blank. Basically, your options are, is it less than, greater than, equal to? Those are your choices. So think about that for a second, and we're going to demonstrate this. I'm going to represent side lengths with different color here. Let's say I have a blue piece that is 3 units long. I'm going to have a green piece that is 2, and a yellow piece that is 5. Do you think these 3 side lengths can make a triangle? And what I'm hoping that you're going to see is that if I was to lay these up right in each other, those are congruent, they're equal pieces, but as soon as I create any sort of angle, then these pieces are going to come up short. Because they were equal when they were right flush up next to each other, but as soon as I pop them out, they're not staying together to remain equal. So the answer to this question is the sum of any two sides needs to be greater than the remaining side. So let's say I have 5, 8, and 11. Can these 3 sides make a triangle? Well, 5 plus 8 is greater than 11. 5 plus 11 is greater than 8. And 8 plus 11 is greater than 5. So yes, they can. Like we said over here with the 3, 2, and the 5, because 3 plus 2 is equal to 5, the answer is no. They cannot be a triangle. Okay, the next thing I want to talk about is, I'm just going to call it the side angle relationship. Let's start with an example. Let's say I have triangle ABC here. I know AB is going to be 13, AC is going to be 10, and BC is going to be 7. And I want you to order the angles. smallest to largest? Well, I don't know anything about the angles, I just see the side lengths. Well, let's think about this. Think about opening a door, you know? And from the hinge, if I was to open the door just a little bit and that distance between my handle and the door frame, if the door's not open very wide, it's a pretty small distance. But if I open the door really wide, then that's a bigger distance. And so the idea here is that the smallest angle is across from the shortest side. And that means the largest angle is across from the longest side. So if I was to order these side lengths, smallest to largest, well, here's my smallest side, which means that the smallest side is across from the smallest angle. So my smallest angle here is going to be angle A. My next longest side is 10, and so the angle that's across from is angle B. And my longest side is 13, which means that goes with angle C. And that's how we'd order them. I could do this the other way as well. So I can say order the sides. And I can give you, let's say something like that. And maybe I have 50 degrees, 47 degrees, and a 93. And let's just call that JKL. Well, here's my, we're also going to say, we're just going to keep it smallest to largest. My smallest angle is angle L, which means the side that it goes with is JK. Side JK. My next smallest angle is 50 degrees, angle K, so that's going to go with side length JL. And then my biggest angle is 93, which is across from side KL. And there we go. All right. Let's see. We also need to cover, I know. Let's talk about dilations. Okay, I want you to think about, I don't know if any of you have ever had your pupils dilated or what that does, but you think about your pupils being dilated, it basically means your pupil just gets really big. It gets a lot bigger. So a dilation is basically just an enlargement or a reduction. So And we'll just call this triangle ABC. Got a lovely 3, 4, 5 for our triangle here. Well, let's say, okay, I'm not going to make this to scale in the future, but I've already committed. Okay, 6, 8, 10. We're going to call this triangle A prime, B prime, C prime. That just means something has happened from ABC. Okay, notice that this is a dilation, but how can we tell it's a dilation? I'm hoping you answered out loud, kind of like Dora the Explorer, like you just told me. Basically what happens is I can look at each of these side lengths. I say, oh, from 3 to 6, I multiply by 2. From 4 to 8, I multiply by 2. And from 5, I need another shape. From 5 to 10, I multiply by 2. So I can tell that this is an enlargement because, one, the shape got bigger, and also all of the side lengths have been multiplied by the same amount. That amount is what we call a scale factor. Important, so I'm going to underline it in red. The scale factor is always going to be represented by the letter K. It doesn't have units because it's just talking about, well, what am I multiplying by every time? So in this case, to get from triangle ABC to triangle A prime, B prime, C prime, I know that K equals 2. My scale factor, what did I multiply by? Well, if I was to go the other way, you'll see that this is an enlargement. Well, what if I go from triangle A prime, B prime, C prime to triangle ABC? What's my scale factor then? Well, what do I have to multiply 10 by to get to 5? To multiply it by half, and that's a reduction. And a way that we can think about this, maybe I didn't know that offhand. Well, we'll wait till we do another example. But here's a big thing that I want you to know with scale factors. So I want you to just think for a second, is there a way you could tell if it's an enlargement or a reduction just based on the scale factor? So let's say you didn't even have these figures of the triangles. How would you know if it was an enlargement or a reduction? Once again, I hope we had a nice Dora the Explorer moment where you just spoke out and said it. But basically, if it's an enlargement, K is going to be greater than 1. And if it's a reduction, my K, aka it's going to be less than 1. And that's how we can determine. Okay. I can spell. Nope, I'm going to keep it a triangle because I don't feel like drawing more. Okay. And so obvious, right? If I have to find the scale factor from figure 1 to figure 2, I can take any of these side lengths here. So I can take 10 to 3.4. And I need to know, okay, well 10 times my scale factor is going to get me 3.4. And so what we can do is just to get k by itself. And there we go. I could check that with any pair of side lengths. So I could do the same thing and say, 12 times my scale factor gets me 4.08. And divide it by 12, guess what? K is still going to be 0.34. So as long as you pick 2 pairs of corresponding sides, then you should be fine. All right, the last thing that we need to cover, let me fresh slate this. How much battery do we have left? 8%, oh, we're fine. All right. All right. First off, we're going to talk about vocab. The word partitions. That means it's just going to split up the segment. And so what's going on? Let's say I have the endpoints of my segment here. And I mean, obviously, your segment is not going to be just, a horizontal line. It would have some slope to it on a graph, but I think visually we can just, here are my endpoints, and we're going to partition into a 2-to-1 ratio. So how many pieces does that mean I have in total? Well, this means that for every 2 pieces of one segment, I have 1 piece of the other. So this means we have 3 pieces in total. And so basically, I need to split my segment into even thirds. And this is just going to be a rough guess, because 1, 2, 3, 4, 5, 6. Yeah, because it's 10. And you don't have to be so specific. You can just sketch it out. That's fine. I'm going to be a little bit more picky. It's fine. Somewhere in there. Okay. Point is, I have 3, and this point is going to split the segment into 2-to-1, which means I need 2 pieces over here, and I need just 1 piece over here. So I am looking for the coordinates of this point. We're at -2, 3, and we're at 7, 30. All right, well, here's the deal. I'm going to start by taking a look at my x-coordinates. And what is the total distance between my x-coordinates? From -2 to 7, that's a distance of 9, and I'm splitting up into 3. Which means I can just take that 9 divided by 3. So that means for each of those pieces, my x distance is moving by 3. So -2 plus 3 gets me 1. 1 plus 3 gets me 4. And then 4 plus 3 gets me 7. Great. Let's do the same thing with the y's. From 3 to 30, that's a total distance of 27. So that means per piece, I have 3 total pieces that I'm looking at. So that means I'm moving 9 every time. So 3 plus 9 gets me to 12. 12 plus 9 gets me to 21. And then 21 plus 9 gets me to 30. Great, that checks out. And so, hey, look at that. This was the piece, this was the point I was looking for. So my coordinates are 4, 21. And that's it for that. I think you'll be okay. I think the biggest thing is just realizing that to figure out how many pieces to split it into, you just need to look at the total of your ratio there. I know this was kind of a random lesson, but it builds into what we're doing for the rest of the unit.